Let's get started. Last time we talked about titration curve of acid and base, right? So in the case of compound acid that has only one proton, you're only gonna get one buffering region, okay? So for a polyprotic acid, that means it has multiple hydrogen to give away. It's very likely you will get multiple buffering region. So you go from, because they have several pKa. So similarly, you can do the same thing for base. For example, some compound has multiple amines. For example, quinine, it has two types of base site, okay? So if you can use the definition of a Bronsted acid and base, right? So it's ability of these element to accept a proton or give away a proton. All right, so when we are doing titration, where you see a sharp increase in pH, the middle point will be your equivalence point, okay? And so conventionally, you would use a acid-base indicator when there's a chemical structure change due to protonation or deprotonation. Sometimes you will get a color change. So it has to do with the resonance structure, which we will talk about it more when we talk about organic chemistry. But because I changed the order of our class a little bit, so I'm not going to talk about the acid base. But when you read the textbook, there's a section on various type of indicators. Okay, so the most important part is to recognize there are going to be the conjugate acid or conjugate base pair. So when you have both species are present, you have to account for both of their color. So ideally, it would be nice to have an acid or base indicator where your color change from completely colorless to a very highly colored solution, okay? But that's not always the case, all right? So it really depends on the range that you're looking at. And nowadays, people will use a pH meter to monitor the pH, and you don't have to do titration anymore in a real laboratory. Instead, you will use an automated titrator where as long as you have your right solution, so for example, the 0.1 molar sodium hydroxide or 0.1 molar HCl, and it will automatically titrate and create these curves, and then you can get the Ka value. And then some of you might wonder, okay, how is this relevant to our daily life? So I want you to take a minute, talk to your partner, discuss why does titration or why does pH value matter so much in our daily life. So usually we want to be at equilibrium, right? So when there's a buffer system, the multiple equilibrium will be turned on. So think about the Jalil principle, right? When you change something in your system, it will want to go back to the original equilibrium. So one example of a natural buffer system is natural water. So if you think about lake, stream, right? So let's say there's acid rain, okay? Because we're producing a lot of pollutant from combustion or fossil fuels. There are going to be some sulfur species, some nitrogen species. And once you burn them, for example, for sulfur, it will generate sulfur dioxide, right? And then once it's dissolved in water and under certain condition, it may oxidize and generate sulfuric acid, right? So when you have acid rain, okay, so this is a unnatural system, okay? So because usually you don't get combustion so easily. Maybe you get wildfire every once in a while, but you don't get combustion that easily. But with the human activity, you have a lot more output of these we call it acidic gas, okay? So when you have acid rain, okay, so in the lake and in the river, there's a lot of mineral. So normally they present as a carbonate species. Okay, so when we think about the pH change slightly, there's a second equilibrium that's going to come in. The carbonic acid will decompose back to water and CO2, right? So the pH value will shift back. Okay, so you can also think of having a lot of CO2 dissolved in water. It's going to react with the mineral, right? So then you are going to get a precipitate. That's why we need to learn about the KSP, right? So the concentration of each species will determine whether it's present in our reaction system or not, right? So when we think about the Q value, we think about calculating the K of our system. If you change the one concentration, you can use these equilibrium constants to estimate whether this reaction will keep going or not. When it precipitate, we don't really care about it because it's out of your system, right? Then you can do the calculation and figure it out whether this system has reached to the equilibrium or not. So in other type of system, for example, in drug delivery, okay, so I think some of you may have heard of DNA or RNA therapy, okay, so nowadays this is the next generation therapy where you're able to deliver DNA or RNA into the cells, okay? So one example is that when we talk about DNA and RNA, right, these are charged species, okay? So usually they have negative charge, okay? So you can think of this as a particle or that has negative charge. So when negative charge see positive charge, what's gonna happen? They're gonna have some interaction among them, right? To do this, so typically our body pH will be 7.4, right? But in some area of the cell, the pH is much lower. So it can go down to about 5.5. So not to mention in your stomach, that's even lower, it's less than 1, right? So you have a lot of HCl for food digestion. So going back to this huge difference in pH between the normal tissue, such as 7.4, or in a certain part of your cell, it will be about 5, right? So that difference in pH, it will change your equilibrium, right? It will change the binding constant between a positive charge and a negative charge compound, okay? So potentially you can form a complex, which you can think of it as a precipitate, but in some cases, it's a hydrated precipitate. So it's in between the precipitate and a fully soluble species, right? So once the pH change, the solubility, you can think of it, the KSP value change. So you can release your DNA or RNA into a certain part of the cell. Okay, so this is one example of how the difference in pH can be used to deliver something. So I just want to mention that. Okay, so now I want to talk about homework problem for a little bit. And I know some of you already got all the questions right, but there's still a lot of you miss problem 115 and problem 184 for chapter 18. So the reason why I talk about 16 through 19 is because we're all talking about equilibrium, right? So we start from chemical equilibrium, then we talk about how can one calculate the pH value based on Ka and Kb. So the most important part is you have to remember Kw is a constant at a certain temperature, okay? So Kw imply the amount of hydronium and hydroxide. This is the equilibrium constant for water, and it is constant at 25 degrees, okay? So Kw, you can find a compound's Ka and Kb based on this equation, okay? This is a very important equation. And for water, the amount of each is balanced, okay? But when you're adding, so for example, sodium acetate, we talk about this example over and over, it's gonna, because if you're adding pure sodium acetate, we know the group 1 and group 2, most of them, they will dissociate completely, right? So your acetate ion is going to pick up some proton from the water, right? So when you remove some of the proton, that means you're left with hydroxide. That being said, we can define Kb where B is the base. So when we talk about Kb, we care about how much hydroxide. So again, when we add pH and POH together, that would naturally be 14, okay? So once you calculate, you can calculate pH and you can calculate POH. For the problem 18.115, we talk about sodium, it's a question about sodium hypochlorite, okay? So this is a common chemical used as a disinfectant, and it's very popular nowadays with the COVID-19 threat. So everybody wants to kill all the microorganisms with this. This is also present in the swimming pool, okay? So this is the type of chemical that people will use because it's able to oxidize a lot of stiff organic compound. Its function as an oxidant, okay? But this is a really good example because this is very similar. So you already seen sodium acetate so many times. So this is just another anion, just another identity. So it shouldn't be that hard. So if you want to look into how to do the calculation, you can look at your page 797. Okay, so it has a detailed table of all the Ka, right? So if even you can't find this table, I mean, you read the book, right? Even you can't find this table, you can look up online to figure out what is a Kb value. So from this table, you can get Ka. So when you're given a weight percent as a chemist, we think about things in mole, okay, in mole per liter, okay? You can, if you want, you can also calculate, I mean, a more relevant quantity to chemists is millimole per mil, right? Because usually you won't work with a very large scale reaction. You would deal with reaction has a volume less than 100 mil. But it's essentially as a big M. So when you get a weight percent, we are going to make simple assumption, okay, such as density is 1 gram per mil, right? So it simplifies a lot of stuff. When it's given 6.5 weight percent, usually we will assume this is called weight percent, right? And then by using the assumption of 1 gram per mil for the density, that become mil. And then we just need to convert it into mole or millimole, okay? You be careful with your calculation, okay? So if we divide this by the formula weight, we can get a value, right? So then you can get the concentration. If you do the math, you can get this concentration. And then since in this case, if we take the pKa value, right, we can get, like the book said, it's 2.9 times to the 10 to the negative 8, right? So you can get a pKa value of 7.51. And from that equation, right, similarly, I mean, Ka and Kb is a measure of how much OH or H can be produced, right? So you can figure it out your Kb value. So when we dissolve this in a solution, it's gonna pick up some hydrogen from your water, right? So let's go back to this equation, okay? So I think as a good practice, always write down the equation, okay? Don't just think in your head. It's because a lot of time that's where you can start making mistake. So this is completely dissociated. So I don't care about the cation anymore. So it's gonna react with water. Then this is where this equation coming from, right? This is the measure of OH. And this is your BH plus term because it pick up a hydrogen. And this is your concentration, right? So from the weight percent, we already know what's our concentration, which calculate out to be 0.873 mole, right? And if we look at our equilibrium constant, right, the Kb is about 3.3 to the negative 7. Okay, so that is a very small value, okay? So when we're talking about acetic acid, okay, CH3COOH, when we dissolve 0.1 molar of it only 1% of it dissociated, and then that has a Ka of 10 to the negative 5. So in this case, it's off by a 2 order of magnitude, right, from the negative 5. So even less amount will actually pick up the hydrogen from water, right? So we can make a simple assumption. The concentration of this changed very little, so that simplified our calculation. So we know when it reacts, it forms certain amount of this and hydroxide, right? And then their concentration are equal. And we know this X is likely to be very small. So to simplify our calculation, we can take away this term, okay? And we can set up our Kb, it's equal to X squared, right? Divide by, and then we solve for X. This X is likely to be a very small number. Then once you get the X, you get the POH, you can calculate pH. Okay, so I mean, a good way to work on these problems is to actually work through the example problem in your textbook. All right, so let's talk a little bit more about the sodium hypochlorite, because I know we didn't really talk much about chapter 14, right? Sodium hypochlorite is a very interesting compound. It has multiple reaction pathways. For example, we already know we dissolve this, it will generate very small amount of this compound and hydroxide. So most of the time, sodium hypochlorite is sold in as a basic solution, okay? Because when you're in a very acidic environment, this is going to form, right? So one can do this, we can bias the equilibrium by adding a lot of strong acids such as HCl and decrease your solution pH till 1 or 2. And at that point, there's so much hydronium ion present, right? So it pushes the equilibrium, it's gonna force the formation of this acid, hypochlorous acid, okay? So when there's HCl present, it's gonna undergo a redox reaction, okay? So you're gonna generate chlorine. So that explains why does the pool have a distinct smell, like you're smelling chlorine, okay? And this is a very toxic gas, but when it's present in a small amount, it actually doesn't hurt, right? So in some pool, when they mix up their concentration incorrectly, or you would say there's so much chlorine in the water, it will hurt your eye, because when the concentration is high enough, it starts attacking your skin, right? It starts attacking your mucus system. So for example, your eye will hurt, right? Because it's reacting with the proteins present on your eyeballs, right? All right, so when there's chloride ion, it can also form complex, similarly to what you have seen for iodine. So iodide, and it forms a triiodide complex. And then in some cases, when there's a lot of acid present, it can also become the chlorate form. This chlorate is also a good oxidant, right? It wants to give away that oxygen. If we left the bleach bottle open to air, it also potentially will react with the CO2 that is present in the air and form sodium carbonate. Yeah, so it will react with carbonic acid and form sodium carbonate and some of this chlorous acid, hydrochloric acid. Okay, so some of you might have heard explosion happened at the pool. Okay, when they're a common cleaning chemical, another common cleaning chemical people use is ammonia solution, right? So you bubble ammonia through the water and you will get ammonia. And this aqueous solution is a common cleaning agent. So when you mix accidentally, I mean there's news, when someone accidentally mix ammonia with sodium hypochlorite, and they get an explosion. And that is because when you mix these two compounds together, it's going to form chloroamine. There can be multiple exchange reactions until you get this. And under certain conditions, this will spontaneously decompose to nitrogen and chlorine. And especially after people mix a solution to avoid evaporation, and which will cause the change in your concentration, you will cap it, right? Then you are in a closed environment, so eventually you get pressure build up. When your pressure is too high, your container cannot contain it anymore, you get explosion. Now we'll talk about problem 184. That is a question that is more relevant to the application of our acid-base chemistry. Okay, so like I said, recognizing what does pKa or what does Ka really means. When we have a larger K, that means the product is favored, we have a lot more product. Okay, so when we're talking about acid-base, acid produce proton, base produce hydroxide, right? If we look at the pKa value, so we think about the magnitude of these equilibrium constant. When someone says, oh, the pKb is 5.1 and pKb of the other nitrogen is 9.76, if you don't have an idea, okay, what does that really mean? You can calculate the Kb from the pKb, right? So for the pKa 5.1, that will give you Kb of 7.9 to the 6. And then for the pKb of 9.76, if you do the math, so this value is much smaller compared to this. So that means this is a stronger base. This is going to be more happy to grab a proton from water than this base. Okay? And when their order of magnitude is different by a lot, we know this will be the dominating nitrogen to capture hydrogen or proton, right? So this problem is to get you to start thinking about, okay, what does that really mean? So we can do the similar calculation, right? So if you want to have a practice, you can look at the page 822 and the sample problem 18.12. Okay, it actually worked through the calculation. So read the book, please. This is the best way to learn, okay? And then so if you solve for x, you can figure out this problem. The second part, the problem B, I mean, simply you just do the math again. Okay. Then the C is the more challenging one, okay? So it talks about quinine salt. There's a lot of pharmaceutical compound. I mean, in order to increase the solubility, you will make a salt version of it, okay? So it's either about adding acid or adding base, all right? So there are some compounds that will have, for example, sulfonate group, okay? So you can produce a salt version of it. It's gonna be better than its acid version. When we talk about this, one way to think about it, we already know amine, pyridine, they're a weak base. And to estimate the pH value of salt, right, we will think about the conjugate acid and conjugate base, okay, whether it is a strong acid or strong base. For a weak base and a strong acid, we know HCl is strong acid, then you should have a sense that you're going to likely to produce a slightly acidic solution. This is a good way to check your answer. So if you're getting a weird value that is super basic, that's not going to be right. And from the previous calculation, you already know, okay, what range of pH you will get. Okay, when you're adding a salt, you probably will be expecting an acidic solution. I'm going to stop here and let's think about what's the pH value of this solution. So we talk about ammonia. So you can use the table 18.8 to figure it out this. I want you to discuss with your group member. Is it going to produce an acidic or basic solution, and why? So it basically summarizes all the conditions that you may run into. You do not have to memorize this table. I think it's better if you try to understand the origin of these statements. Okay? So for example, you can remember that when you mix strong acid and strong base, it's going to give you a neutral solution, okay, neutral salt. So when the weak acid is used, strong base will dominate this equilibrium. So if you look up on top of this page, we can look up the Ka value, right? For ammonium, NH4 plus, it had the equilibrium, a Ka value down on the order of 10 to the negative 10, right? For cyanide, it has 10 to the negative 5, right? And we know the larger the value, that means you're producing more of these products. Sorry, I made a mistake. The Cn is Kb, okay? So by doing this, we know amount of acid generated is much less than the hydroxide. And also recognizing that HCN is a weak acid, okay, based on the Ka value that we discussed before. And we know ammonium, it could come from ammonium hydroxide, right? So when you have a lot more hydroxide in the system, it's going to be basic. Okay, that makes sense? Okay, so going back to the problem 18.184, later on these calculations are quite simple, okay? You just have to follow the step, okay? Know how to figure it out molarity from weight percent solution. Okay, then you can make some assumption. This book has a lot of example problem. It will tell you how to check the assumption, okay? When we're dealing with a very small rate constant, it's okay to omit it in the equation because the overall change in its concentration is so small, but we care about the product. So that's I think that's all I have for today. And we will briefly touch on the electrochemistry. For electrochemistry, that will be chapter 21. So anode and cathode. Okay. In physics, when we talk about electromagnetic, the definition is slightly different than the chemist. So sometimes we will talk about positive and negative, or sometimes we'll talk about cathode and anode. Do not get confused by this cat. It's different than cation. So the way I remember what's happening with these things is, even though in English we talk about redox reaction, right? Redox, you will see this word all the time. But in Mandarin, we'll say 氧化还原, right? A way I memorize this is, because these are definitions, there's no good way to understand, because people define saying where oxidation happened is anode, where reduction happened is cathode. So the way I memorize it is A is in front of C, right? So in Mandarin we say 氧化还原, right? So A, that has to be oxidation. This has to be reduction. Okay, the book also has a weird way with saying you can remember a white cow. So ox is an alternative name for a bull, a male cow. So they say remember the anode, okay, and then the red cat, okay, red for reduction. So that's another way to memorize it. Because A comes before C, so whenever I remind myself is, okay, this is where the electron is gonna flow, okay, and then so this is reduction. And then if we think of a copper zinc system, so this is a very classic example where you have zinc and copper as your electrode. And then when zinc, we know is a more active metal, it's going to be able to reduce copper into its elemental state by sacrificing itself, changing its oxidation state from 0 to 2 plus. So it's losing electron. Once it loses an electron, this is the oxidation. Okay, and then the other way is the reduction. Okay, so by knowing the electrons flowing from anode to cathode, so you see the connection here, oxidation and where the electron flow. Okay, so chemistry is all about electrons because that has to do with how bonding can form. When I form a covalent bond that is sharing electrons. when there's some interaction, very strong electrostatic interaction, that's ionic bond. All right, so I think that's all for today, and we will talk more about electrochemistry for the next 2 to 3 period.